Understood? That is called as a prismatic bar. Now we want derive an expression for axial deformation. Axial deformation means what? If the bar is there, then this is the axis. Along the axis deformation, either it may be extension or it may be compression, okay, either it may be extension. When you apply the pull force, extends. When you apply the push force, it will compresses. Okay, that is called as axial deformation. We want an expression for that, how much this extension is there, how much this reduction is there. For that they want one formula, that is called as that. For that we have derive an expression for axial deformation in prismatic bar. Actually speaking, this we already done. In Hooke's law only we have derived it. But separately they are asking here, therefore we will derive it here. This question you can expect in the examination for 4 to 5 marks. Okay. Now look at here, for some theory we need to write. For exam point of view, you need to write some theory. Just I will dictate here, pause the video and go on writing this one. Okay, now the first one, let us consider a prismatic bar of length L, write down in terms of words. Okay, here let us consider prismatic bar of length L, cross sectional area A, okay, and subjected to a pull of P, okay, P axially, comma, as shown in the figure. Now see, this is as shown in the figure. Next point, below this one, okay, the material will have Young's modulus E. Next point, next line, after axial deformation, change in length is read as delta L. Over. Next, according to Hooke's law, stress is directly proportional to strain. Therefore, stress is equal to Young's modulus into strain. Okay, call it equation number 1. Now we know that stress is equal to force divided by area, call equation number 2, and strain is equal to change in length to the original length, call equation number 3. Now substituting 2 and 3 in 1, what you will get? P by A equal to E into delta L by L. Then therefore rearranging, after rearranging, what you will get? Delta L equal to PL by AE, over. Okay, this is an expression for axial deformation in prismatic bar. Write down this derivation. Now welcome you all, dear students. In the last class we discussed about axial deformation, that prismatic bar. Now in this class we will derive an expression, one more derivation. You can write the heading as derive an expression for, 1 minute. No, we'll discuss that derive an expression for, put the heading, derive an expression for axial deformation only due to self weight, okay. This is a derivation. This is the heading, and let us consider, you can write down the points here. Let us consider hanging prismatic bar. Write it in words first. Okay, let us consider hanging prismatic bar with cross sectional area A with the length L with the material property Young's modulus E. Okay, and the prismatic bar which has unit weight gamma and its complete weight complete weight as a W. Unit weight means it's like a density. It is like a density. Okay, and it is a complete weight means just we are measuring the weight of that. Let it be W and this be gamma. Okay, na? These informations we got. Now when we hold this particular bar in this way, then because of the self weight we will observe some elongation in the bar. That elongation we will call delta L, but this delta LS will call, because this is a elongation due to self weight, therefore this is a delta LS. We want expression for this delta LS, but no force is pulled here, therefore it is very difficult to understand why it is extending its length, right? That is because of self weight. But when I consider this plane, at this point self weight is only this much. When I consider here this much, when I consider this support, the entire self weight is acting. Therefore the self weight is varying from here to here, and which is actually that making this extension, that is varying from here to here. Therefore I will consider a small strip in between. This is a very small strip. Therefore the thickness of the small strip I will call it as a dx. This is a dx. Then where exactly this strip is situated, that I will call it is a x distance from the bottom. This small strip is situated at a distance x from the bottom. Then what is the cross sectional area of the small strip? Again, because it is a prismatic bar means from here to here it is same, therefore cross sectional area of the strip is also A only. Okay, now if I write the free body diagram for this small strip, how it will be? That small strip will be like this. This is a small strip, and this small strip is in equilibrium. Yes, it is in equilibrium, even though it is in the middle, but it is in equilibrium. Then this small strip is pulled by this much of load. I will show you with a red color. See, this much of bar is there, no? This much of weight which is pulling it down. This much of weight is pulling it down. Therefore the downward force will be Wx. Wx means the prismatic bar of length x. This is the Wx. Then if it is in equilibrium, then I have to call this will be again Wx. This small prismatic bar, this small strip what we considered, its thickness or its length is dx. Its length is dx. And the weight of the small strip is ignored. Why? Because it is very small, therefore the weight of the small strip is ignored. It is not considered into a vertical direction. Okay. Now if this small strip extends its length, if this small strip extends this length, let us consider that extended length of the small strip as a delta Lx. Then I can write the expression for this delta Lx very easily by using the prismatic bar method. Delta Lx equal to PL by A. P here is Wx, L here is dx, then A here is A, and E here is E. Okay, now this is your small strips extension. Now here this Wx is there. No, how to get this Wx from here to here? That I will write here. Always the density is equal to weight by volume, weight by volume. If I consider a small weight, then the volume is also small. Then this Wx I can write it as Vx into gamma. Vx into gamma. Then what is this Vx? Vx is a small volume which is shaded by a red color. Then this volume I can write it like area into x. That is your area into length is a volume into gamma. Now I got Wx in the place of this I can write. Therefore here Wx means Ax, gamma if I write Aa gets cancelled. Therefore it will be gamma x dx divided by E. Only this much is left. AA is cancelled. Then this is expression for a small strip. If I want the expression for the complete diagram, then I have to integrate the entire thing. Then integration of delta Lx equal to gamma is a constant and E is a constant. I will take it out. Then integration of x dx. Then the integration of delta x will be delta Ls elongation due to self weight. Then this gamma and E will be constant. Then this integration we are doing from 0 to L, because this x is varying from here 0 till it is varying to L. Therefore it will be x square by 2. Then the limits are 0 to L. Then if I substitute upper limit and lower limit, I will get an expression. Below this you write, I will get an expression delta Ls equal to gamma by E into L square by 2. L square by 2. This is an expression for elongation due to self weight. You can write it like gamma L square by 2E. Now what is gamma? The entire weight if I want to convert, then the same formula I will use, gamma equal to total weight divided by total volume. Then total volume is what? Total volume is area into length. Now if I substitute here gamma L square divided by E is this gamma I need to write, in the place of gamma I need to write W by AL. Then this L cancels, therefore you will get delta Ls equal to WL upon 2AE, because this 2 is also there. Then this expression you will get it. Either you can use this expression or you can use this expression for elongation due to self weight. This is very, very important derivation you can expect for examinations. Welcome back, my dear students. Today we will derive one more expression, very important expression, that is, write down the heading, derive an expression for axial deformation of circular tapered bar, subjected to axial pull or push. I will consider for the problem, for the derivation, pull. Okay. Here this is an expression. First we need to write some information, that what we are considering, what we are assuming and all. That I will dictate. Whenever you want, pause the video and go on writing that content. Okay. Let us consider circular tapered bar of diameter d1 and d2 as shown in the figure. Full stop. Let P be the tensile force which is pulling the tapered bar. Full stop. Let E be the Young's modulus of the tapered bar. Okay, now that figure we have to draw. See here, the figure is something like this. Tapered means that cross-sectional area is not constant. It is continuously changing from one point to other point. But the thing is, this change is constant. This change is constant. Okay, now let us consider this is the axis of the bar. This is the axis of the bar, and this bar is pulled by the force P, and this bar is pulled by the force P. Okay, and here the total length of the bar is L. The total length of the bar is L. Okay, now, and the diameter, see here, this is a circular tapered bar, means if I see this way in a front view, in a side view, I will get this circular bar diameter as a circular like this, and if I see this side, then I will see the circular as this side. This means that this is a circular tapered bar. Okay, now this diameter I will call it as a D1, and this diameter I will call it as a D2. This diameter I will call it as a D2. Then again this cross-sectional area is completely changing, continuously changing from one end to other end. Therefore, I will consider, I cannot solve it directly, therefore I will consider a small strip here in between at a distance x from this end. X from this end. Okay, this is your small strip. And this strip dimension thickness is dx. This one thickness is dx. Okay, and this small strip diameter is d. That small strip diameter is d. Now what all notations I have taken here I can list here. D1 is the diameter at the one side, D2 is the diameter at the second side, and L is the total length, and P is the tension force, P is the pull force. Now what else? The small strip I considered. Small strip thickness is the dx. Small strip is situated at a distance x, and small strip diameter is the d. Now I need to express this diameter d in terms of d1 and d2. In terms of d1 and d2. For that reason, for your understanding purpose, I will simply modify this bar. If I put this bar on the horizontal surface, then it will be like this, right? If I put that one in a horizontal surface, approximately it will be like this. Then this will be your d1 and this will be your d2. Okay, then my strip is here. That strip diameter means this height is how much? It is your d. Now this d I can write it like, see here, something like a d1 plus, we will call this one as some n. So n is some notation I give. Then what is the diameter here? The diameter is d1 plus n. d1 plus n, correct? This is a d1 and the upper triangle is n. Then if I draw that triangle portion here, then this distance is a n, and this distance is what? This is d2 minus d1. This distance is d2 minus d1. Now this n I want to express, and this total length is L. This total length is L. Then this n I want to express. Okay, now similar triangular method says that bigger portion is d2 minus d1, bigger length is L, smaller portion is n, and smaller length is x. Then what I want? I want n. Therefore n equal to d2 minus d1 by L into x. This I will get it as a n. Then here what is the d? D equal to d1 plus d2 minus d1 by L into x. This is very big expression, right? For that diameter it is a very big expression. Every time I cannot write this one. Therefore, for substitute I will consider one substitution so that my work become easy. Therefore, d equal to d1 plus k into x I call. K into x. Then what is this k? Here the meaning of k is d2 minus d1 divided by 2. This is your expression for k. Now you came to know that what is the diameter and what is the k here. This is a substitution. After that, now this small portion is there, no small strip is there. That strip I am going to write it here. Let us consider this is a small strip and this is a small strip. This small strip is also pulled by P. Okay, and the small strip dimension is dx. Small strip dimension is dx, and its diameter is d. Its diameter is d. Okay. Now, if this small strip, actually this portion it might be like this, but it is a small, therefore I can assume like a straight one here. Means it look like a prismatic bar. Therefore, the elongation of this small strip is delta Lx, small expansion, that is equal to PL by A. P is a P, L is a dx divided by A is pi by 4. Instead of writing here 4, I will write it to the numerator. Mathematics it is. Divided by 4, pi by 4 d square into E. Then what is the d? That I will write 4p dx divided by pi. What is the d? Go back. D is a d1 plus kx. D is a d1 plus kx square into E. This is for small strip. If you want for bigger strip, then I need to integrate it from 0 to L. This also I need to integrate it from 0 to L. Then this if I integrate, then I will get a delta L, and this one here 4p is a constant, take it out, and pi E is also constant, take it out. Inside what is left is 1 by d1 plus kx square into dx. In mathematics you should know that 1 divided by a plus bx whole square integration 1 plus into dx. Its integration is minus 1 by a plus bx into 1 by b. This is the integration of this one. That I will write here, that is a 4p by pi e into integration, this is of course 0 to L, integration 0 to L. This portion, sorry, integration is over now. I will do the integration directly, I will write it, bracket it is. Then here what I have to write, this minus I will put it outside, minus outside. Inside I can write 1 divided by d1 plus kx into k 0 to L. Now minus 4p divided by pi e into, if I substitute upper limit here in the place of x, then it becomes 1 divided by d1 plus kl minus, if I substitute the lower limit, I will get d1. X equal to 0, this becomes 0, d1. Okay now? This has happened, and this k is there. Now that k I will take it common outside, that k I am writing it outside. This I got. Here this minus sign is there, that minus sign I will send it inside. When I send this minus sign inside, these two will interchange. Okay, that will be 4p by pi e k into 1 by, what is that, d1 minus 1 by d1 minus 1 by d1 plus kl, right? d1 plus kl, this I got. Then what is this entire term I will look at here. You just look at here, d1 plus kl. See, what is the d1? d1 is the d1. K is what? d2 minus d1 divided by l. And then what is l? L is a l. Then this cancel. This will be d1 plus d2 minus d1. This cancel. Therefore d2. Means in place of this I can write d2. Therefore it is 4p by pi e. Then what is this pi? Leave it, later we'll see. Then here it becomes 1 by d1 minus 1 by d2. Okay, now I will take a LCM. 4p by pi e k into d1 d2 divided by d1 minus d2. Sorry, ulta, reverse it, है because 4p by pi e k into here d1 d2 and here it will be d2 minus d1. Now 4p as it is, pi e as it is. What is the k? K is the d2 minus d1 divided by l into d2 minus d1 divided by d1 into d2. This and this cancel. L in the numerator to numerator comes to the denominator to denominator comes to the numerator. Therefore the final answer will be 4p by pi e d1 d2, then here L. This is the expression for elongation due to circular tapered bar. Thank you very much. In the next class we will derive an expression for tapered square cross section or rectangular cross section. Thank you very much. Welcome back, my dear students. Today we will derive an expression for axial, write down heading, derive an expression for axial deformation of rectangular tapered bar subjected to axial pull or push. This is an expression we need to derive. Now again you start writing some theory, that is, let us consider rectangular tapered bar with B1 and B2 as a breadth at either ends. Let T be the thickness of the rectangular taper bar. Let L be the length and E be the Young's modulus of the rectangular tapered bar as shown in the figure. Now see here, it is like the same way. In a side view it looks like a circular tapered bar only, this way, but in a side view if I see in this perpendicular to this view, if I see, then it looks like this. Then here it is a T thickness it is, and here also it looks like rectangle. This is again, it is a T. Okay, then this is pulled by the force P, this is resisted by the force P. Okay, and the total length is L. Total length is L. Okay, and here cross sectional area is changing from here to here, therefore I don't write a cross sectional area. Then this breadth is the B1 and this breadth is the B2. This breadth is B2. Now this is the axis. This is the axis. Okay. Now I will consider a small strip here. This is a small strip. Small strip here. And that small strip, if I write, sorry, the height or otherwise the breadth of the small strip, I will consider it as a B. That is just a B. Then if I put in the horizontal surface, it might somewhat look like this, and this is a B, and this is a B1, and this is a B2. Then here I will get one small triangle, and this B I can express it as B1 plus M. This is a small portion, that is a M. Then that M can be got by a similar triangular method. This is a M, this is B2 minus B1, this is total is L, and this is X. This is situated at a distance X. Okay. Now by similar triangular, bigger is a B2, bigger height is a B2 by minus B1, bigger length is a L, then smaller height is a M, smaller base is X, then M equal to B2 minus B1 by L into X. This is M. That M, if I substitute here, this becomes B1 plus B2 minus B1 by L into X. Every time it becomes very difficult to write this much of big expression, therefore I will substitute in this place K. Therefore I will get B equal to B1 plus Kx. This I got. Now this small portion, whatever that is there here, this small portion, if I take and draw it separately, it look like this. Small portion look like this. Then the small portion thickness is dx, and which is also pulled by the force P, and its height is B. Its height is B. Then the elongation due to P for this small portion will be look like a prismatic bar. Therefore that is a small elongation delta x, that is equal to PL by AE. P is a P, L is a dx by A. A here is, this will be something like okay, this is thickness, it is, this is a T. Therefore here the area is B into T. This is the T, B, and this is the T. Therefore this will be B into T, and E will be E. Now here this P I will write it dx as it is, and then T as it is, E as it is. B means what? B1 plus Kx. This is for small elongation. If I integrate it from 0 to L, if I integrate it from 0 to L, then I will get the total elongation. Total elongation equal to the common things, constants which I take come outside, P and T and E are taken outside. Then inside 0 to L, 1 by B1 plus Kx into dx. You should know in the mathematics, integration of 1 by x is log x. Integration of 1 by x is log x. The same way, integration of 1 by a plus bx is equal to log a plus bx into b into B. Okay, sorry, here this is not into, this is here x is denominator, no, therefore it is also denominator B. This B and this B don't confuse, this is a formula B. Here A means B1, B means K1, X means X. Therefore this P, T, E outside. Then if this one is integrated, then this becomes log. Log means log base E it is. Therefore log base E into B1 plus Kx into 1 by K, that I will put it here. This is from 0 to L. Then if I substitute here, it becomes P by TEK into log base E B1 plus KL minus log base E B1. Is this x equal to 0? Okay. Now here that B1 plus KL, that I can write it like B1 plus what is K? K is a B2 minus B1 by L into L. Therefore LL cancel. This is B1, B1 also cancel. B2 means in the entire place I can write it B2. Now come back, this entire space I can write it B2. Therefore this expression becomes P by T E K into log base E B2 minus log base E B1. Okay, this become P by T E K into log base E B2 by B1, logarithmic property. Then what is K? I will substitute that TE, K is B2 minus B1 by L, it will go to the top and this become log base E B2 minus B1. This is an expression for delta L. Over. Okay, in some textbook they will write it like PL by T B2 minus B1 E. Here instead of log base E they will write it like ln B2 minus B1. This is an expression for elongation due to rectangular tapered bar. Elongation due to rectangular tapered bar. Thank you very much. And from tomorrow onwards we'll solve many problems. Thank you. Derive an expression for volumetric strain. This is the fifth derivation. Let us consider one three-dimensional body. This is your three-dimensional body. Okay. Now let us consider this is L, this is the B, and this is the D. Then total volume will be what? We'll write total volume, total initial volume is L, B, D. Right? Now I will apply some force to this one in all the direction, in X direction, in Y direction, in Z direction. I will apply the force. Then it will yield. It will yield means its volume will increase. Its volume will increase. That volume may increase in lengthwise. This is the L direction. Means this will be a delta L. Okay, delta L means not only that length, it will be a throat. Like that, it may increase its dimension. Okay, then delta L is increased. Then how much length, how much volume is increased here? This is the delta L and D into B. Therefore volume increased in L direction. L direction is how much? That is delta L into B into D. Okay, like that it will increase in D direction. It will increase like this. This is a D direction. Okay, it will increase its volume in a D direction. Now this is your delta D, and this is, this is a B and this is the L. Okay, therefore volume increased in D direction is delta D into L into B. Okay, like that it will increase in Z direction also, that is your B direction also. It will increase like this also. Okay, it will increase this direction also. Therefore the volume increased in B direction will be this increase. This increase will be delta B, and this is the L and this is the D. Therefore that is your delta B into LD. Okay, then you can come to what is the total volume increased. Total volume increased, that is total volume increased. Total volume increased equal to delta V. This is a increased volume, that will be equal to volume increased in length direction, that is your delta L BD, plus volume increased in depth direction, delta D into LB, plus delta B into LD. Okay, this is the total volume increased. This I can write delta V. Now divide both side by volume. Then divide both side by volume. No alteration. Now we will keep it as it is, delta V by V, that equal to, here this V means what, that I will write delta L BD divided by V plus delta D LB by V plus delta B LD by V. Once again, if you write in this one, rearrange them, then we will write the expression for V here. Delta V by V equal to, what is there? Delta L BD by V. Delta L BD by V. V means what? LBD plus delta DLB by V. Delta DLB by V means LBD plus delta B LD by V. V means what? LBD. Okay, then here they will get cancels. Here BD cancels, and LB and LB cancels, LD and LD cancels. Then left here is delta L by L plus delta D by D plus delta B by V. This is your delta V by V. This is a change in volume by original volume, volumetric strain. This is longitudinal strain. This is strain in depth direction, strain in breadth direction. This is your derivation. Okay, thank you. Now derive an expression between elastic modulus or elasticity and shear modulus or modulus of rigidity. Okay, we need to derive expression between these two constants. Okay, now we'll consider one plane. This is one square plane, then this distance is A and this distance is A. This is subjected to only shear force, shear stress toe here and shear stress toe, like that. This is applied by a shear stress toe. Okay, Actually this shear stress and this shear stress are acting, and these two, the opposite, these two are complementary shear stress we call. Because of these four stresses, it will deform. This will deform. That deformed diagram look like this. The deformed diagram, let us consider, we'll name this one, this is called A, and B, C, D. Let us consider this is a diagonal, draw the straight line, this diagonal BD, and because of the this will deform this way. Okay, it will deform like this, because forces are like this force and this force, which will yield it, means this diagonal BD will shift. This diagonal BD will shift like this. Okay, this shifted point I will call it is B dash, and here I will draw one perpendicular to BD line. Then this point I will call it as F. This is BF. Okay, now this angle will be phi, and this angle will be 45, and this is 45. This diagram looks very small, therefore I will draw it again here. You can see, actually we are interested here only. This is a 45, and this is a B point, this is a B dash, and this is a F point, and this straight line is like this. It has become here D point, right? Now here one more line we will get, one more triangle. The triangle is B dash B A, B dash B A triangle. That triangle looks like this. Those only I am repeating that because that looks very small there in the derivation, in this diagram. And this is B dash B and A diagram. Okay, from these we are going to draw some expressions. Those expressions are, first expression is diagonal strain. Diagonal strain. You already know strain means what? That is a change in length by original length, right? Here if you see, original length is BD. Original length is BD. BD is the original length. Then what is the change in length? Change in length is, to observe that one I have drawn here one perpendicular. This perpendicular is there, means this extra is there. This much extra is called as B dash F. That is your B dash F. Okay, that is B dash F. B dash F is a change in direction, change in dimension, and original length is BD. Okay, even you can write it like a B dash F. Original length will be FD. Both are same. FD and BD both are same because BF is perpendicular. Now here if you see B dash F, where is that? B dash F. This is a B dash F. B dash F I will represent by sin theta here. Then I will write here sin 45 is equal to, opposite is B dash F. Hypotenuse is, this is 90 degree, therefore this is hypotenuse. Hypotenuse is B dash B. Okay, therefore B dash F is equal to B dash B sin 45. Then sin 45 is 1 by root 2, therefore B dash B by root 2 is the answer. This is your B dash F is equal to B dash B by root 2. That I will write here, that is B dash B by root 2 in the numerator. Denominator is BD. Then I will write it BD. Then what is BD? That BD, if you see in this diagram, this is a square, this is A and this is A, and this is BD. This is a D and this is a B. Then what is the diagonal here? Pythagoras theorem, that is A square plus A square is equal to BD square. Then BD equal to square root of 2A square. Therefore A root 2 is a BD. Therefore BD means it is A root 2. This BD I have written A root 2. Then what about B dash B? I will come to this diagram. Here B dash B, this is B dash B. I will represent a tan phi here. Tan phi equal to opposite B dash B divided by adjacent is AB. AB distance is A. AB distance is A, therefore it is B dash B tan phi. Okay, therefore B dash B equal to A tan phi. Here I can write A tan phi divided by root 2. Okay, now this root 2 will come down and this A get cancels. Tan phi by 2. This phi is very small, therefore tan phi is equal to phi I can consider. Therefore this is phi by 2. The longitudinal direction, diagonal strain is equal to phi by 2. Okay, this expression I got here. Then consider diagonal strain is equal to phi, that is the shear strain divided by 2. We know that shear stress is directly proportional to shear strain, and shear stress is equal to shear modulus into phi. Therefore phi is equal to tau by G. Here I can write phi means it is a tau by G, and this 2 remains as here. This is a diagonal strain expression. And we have one more expression for diagonal strain. That strain will work out like this. Look at here. The plane was like this and it was subjected by a toe and a toe here, and complementary shears toe and toe here. Because of this, it will yield like this. It will yield like this. Therefore, if I consider this is applied as a normal stress to this plane, then I will draw another diagram this way. Then here it will be toe and this is a toe, and here it will be a somewhat compression toe. As per generalized Hooke's law, then I can write it as diagonal strain, that is equal to normal stress, means shear stress is acting like a normal stress by Young's modulus minus mu times another normal stress but which is compressive in nature, therefore minus tau by E. It will be tau by E plus mu into tau by E. Therefore tau by E is a common 1 plus mu. This is also diagonal strain equation number 2. This is equation number 1. I will equate these two, then I will get tau by 2g equal to tau by E 1 plus mu. Tau by E 1 plus mu. This tau cancels. E comes this side and 2g comes this side. 1 plus mu as it is. Then you got this expression. This is the relation between Young's modulus and shear modulus. Thank you. Next one, last derivation in module 1. Last derivation of module 1. Derive relation between Young's modulus E and bulk modulus K. For this I will consider one three-dimensional body. That three-dimensional body will be like this. Now it will be this way. This is a three-dimensional body. Let us consider it is subjected by a force pressure P this direction, and in the same pressure in y direction P and P, and in z direction also P and P. Okay. If that is the case, then the strain in all three directions I have to write. That is, strain in x direction will be for pressure in x direction divided by Young's modulus minus mu times pressure in y direction divided by E minus mu times pressure in z direction divided by E. This is strain in x direction. Strain in y direction is equal to pressure in y direction divided by E minus mu times pressure in x direction divided by E minus mu times pressure in z direction divided by E. Then strain in z direction is equal to pressure in z direction divided by E minus mu times pressure in x direction divided by E minus mu times pressure in y direction divided by E. In x, y, z direction the pressure is same, therefore we are getting same equation in all these three dimensions. If I add all of them, then I will get here epsilon x plus epsilon y plus epsilon z. Then this equation, this equation, this equation, all these three equations are same, therefore I can directly sum it up as 3 times P by E minus mu times P by E minus mu times P by E. This I can simplify further, P by E minus 2 mu P by E. Then if I take P by E common, then I will get 3 P by E taken common, 1 minus 2 mu. This is your volume, this is your strain in x, y and z direction. In the fifth derivation we derived this one. This is meaning of this one is volumetric strain is equal to 3p by E 1 minus 2 mu. And here volumetric strain with respect to bulk modulus, it will be pressure in 3 dimension divided by bulk modulus is equal to 3p by E into 1 minus 2 mu. Then pp cancels, then E comes this side, E is equal to 3k 1 minus 2 mu. This is an expression. This is very important expression. Out of these two equations, that is your previous equation, that is E equal to 2g into 1 plus mu and E equal to 3k into 1 minus 2 mu. Out of these two, one derivation will be compulsory in the examination. And sometimes they may ask this derivation also, that is derive an expression for E, G, K and mu. See, they are asking all four should be there in the, sorry, it won't be there. We can also. All four should be there in the equation. If they are asking this derivation, then you need to look at the marks. Now, if that is the case, then we will write it like, we know that E equal to 2g into 1 plus mu, and we also know that E is equal to 3k into 1 minus 2 mu. Okay. Now, if it is more than 6 marks, then you have to derive this equation and go ahead what I do in this page. If it is less than 6 marks, 5, 4 like that, then whatever I explain here, only that much is enough. Now this is also E, this is also E, therefore I will equate 2g 1 plus mu is equal to 3k into 1 minus 2 mu. Now we'll get inside 2g plus 2g mu is equal to 3k minus 6k mu. Okay. Now what happens? This mu will keep it this side, 2g mu, and this mu term also comes this side, that is 6k mu, and this side will be 3k minus 2g. Therefore mu taken common, 2g plus 6k is equal to 3k minus 2g. Then mu is equal to 3k minus 2g divided by 2g plus 6k. This is your mu term. But we want put that one in terms of E. Therefore, this is E is equal to 2g into 1 plus mu. Then E is equal to 2g 1 plus mu means what? That is 3k minus 2g divided by 2g plus 6k. Okay. Then take LCM. 2g. LCM is 2g plus 6k. This will be 2g plus 6k plus 3k minus 2g. This 2g cancel. Therefore 2g. 6k plus 9k, 3k is 9k divided by 2g plus 6k. Then this will be 18 kg divided by 2g plus 6k. We'll take 2 common in the numerator and denominator, then it becomes 9 kg divided by g plus 3k. This is what? This is E equal to. This is what the relation between E, G, K. Big brothers of strength of material, that is Young's modulus, bulk modulus and shear modulus. Thank you.